This movie goes to Learning Target 7 in Unit 4. You are going to be able to map a triangle with one of the sufficient conditions onto the original triangle, showing that the corresponding sides and the corresponding angles are congruent. So we're going to look at transformations with this. We're going to look at reflection, rotation, translation, and we're going to use a combination of those to map one triangle onto another triangle. Let's take this example right here. We're going to use the definition of congruence in terms of rigid motion. Rigid motion just means that my sizes for the sides don't change and the angles don't change. So a rigid motion is something where you preserve the distance. And so that's what we're looking for to determine whether these two figures are congruent, and then we're going to explain our answer. So what we're essentially looking for here, if I'm going to try to map this triangle ABC to this triangle DEF, I would want to be able to come up with transformations like translate to the right so many units down, or translate to the right and then flip, which would be a reflection, and then a translation. So we're going to look at a composition of two transformations that would take us from one triangle to the other. I'm going to put this back up. We can easily see these two triangles are not even congruent. So it's quite obvious that these did not preserve rigid motion. We do not have a combination that would give us two congruent triangles. So because they have different sizes, and since rigid motion preserves distance, like the distance between AB is not the same as the distance between DE, then there's no sequence of rigid motions that will map ABC to DEF. So therefore the two triangles are not congruent. And because they're not congruent, we're not going to write a sequence of transformations. We just put that we did not preserve the rigid motion. There was no rigid motion, and so therefore triangles are not congruent. So we're going to put this in terms of rigid motion to see if we can map one figure to the other and see if they are still congruent. So I want to see what I can do to this shape, maybe move it, translate it up, and I can see that it will map pretty easily here. So it looks like just a simple translation of to the right and up. So let's see how I need to translate that. 1, 2, 3, 4, 5. Translate 5 to the right. And I know you're not able to do that because you don't have this software, but what you can do is take it point by point. Like translate J to the right 5, then translate M to the right 5, L to the right 5, and just use your vertices. Then you can fill in the sides. So we go to the right 5, and then it looks like we go up 3. So we can map JKLM to PQRS by the translation that has the following coordinate notation. So this is the notation we use for a translation. It means that we're taking the point XY. This is supposed to be an arrow. So XY moves 2. So that X is 5 to the right. So I add 5 to my X value. And 3 up. So I add 3 to my Y value. So that's how I represent a translation, 5 to the right and 3 up. Translation is an example of a rigid motion, so therefore these two shapes are congruent, because when I translate this figure, I did not lose the distances between the two vertices. It's an example of what we call rigid motion. Really, as you could tell from the first problem, that this was just an example of a dilation here. And a dilation obviously does not preserve rigid motion. Okay, I'm going to have you try this one on your own. Come up with a sequence of rigid motions that will map this triangle ABC to this triangle, RST. Keep in mind, if it looks like it's facing in different direction, kind of like this, where it's not just a simple translation, then you're going to need to think about a possible reflection or maybe a possible rotation. So I'm going to have you pause this movie. Go ahead and graph this on a piece of graph paper, ABC, graph RST, and then try to come up with a sequence of rigid motions that will map this triangle to this one. Could it be a reflection and then a translation, or a rotation and then a translation? Go ahead and see what you come up with. Press play when you are finished. Okay, now that you tried this on your own, I think this guy is definitely reflected. So what I'm going to do is I'm going to flip from left to right. That right there would be a reflection over the y-axis. And I feel like I'm pretty close to getting to RST. So if I reflect over the y-axis, then I go down 1, 2, 3, 4, 5. Looks like I map right on it. So I do a reflection over the y-axis and then translate down 5. So I reflect over the y-axis followed by translation. This notation we'll be using later on this year, so I want you to get used to it. A translation means that I'm taking points x, y, and I'm moving them so that x stays the same, so it's x, but I'm subtracting 5 from my y because I'm moving down 5. So this was a simple reflection and then a translation. I would like you to graph these points, D, G, F, H, J, K. See if you can come up with a sequence of rigid motions that will map this triangle onto this one. Press play when you are finished doing that. Okay, when I look at this one, obviously just a simple translation is not going to work. If I look at reflecting this one, that's not going to work. So what I'm thinking is that this guy seems to have some kind of rotation to it. That right there would be a 90-degree rotation. So what happens here is I've got a 90 degrees counterclockwise rotation. And if I look at these points, D is at 2, 1. That's going to be at -1, 2 when I use my when I move the ordered pairs using a 90-degree counterclockwise rotation. This pattern you see right here for 90 degrees clockwise is found on the poster by the clock. We're going to be using that pattern for ordered pairs quite a lot, where it looks like X, Y. In this case, I've got 2, 1 gets reversed, it becomes -1, 2. So that's how you do a rotation. F looks like it's at 4, 1. So this is going to be at -1, 4. Its reflection after that simple rotation. Now, I'm not only finished with the rotation, you can see that I still need to translate up 1. So by doing a simple translation up 1, I've got a rotation of 90 degrees and then a translation of point x, y, where x stays the same, but then I'm adding 1 to y. And that will map this triangle onto this one using a sequence of what we call rigid motion. And that is the end of the movie. I would like you to try the homework worksheet that you'll find on It's Learning for this. And that is the end. See ya.